Hello everyone, welcome to this lecture. Till now we have designed Byzantine agreement protocols assuming n greater than 3t. Okay. Assume and our goal was perfect security. So, a natural question is this a necessary condition if we want to get perfect security, and the answer is yes. So, now for the next few lectures we will focus on deriving this necessary condition, that why this condition n greater than 3t is necessary for perfectly secure Byzantine agreement. So, we will first show that it is impossible to design a perfectly secure Byzantine agreement protocol with 3 parties and 1 corruption. Okay. And then in the follow up lecture we will generalize the proof and use this result, this special case of n equal to 3 and t equal to 1 to show that this condition n greater than 3t is necessary. So, let us try to understand why it is impossible to design a perfectly secure Byzantine agreement protocol with n parties where n is equal to 3 and one of them being corrupt. So, if one of the parties out of these 3 parties is corrupt and say the remaining 2 honest parties have a different input, one of the honest parties have input 0 and other honest party have the input 1, then what this corrupt party can do is that it can always cause the honest parties to conflict with each other in terms of whatever they conclude. Specifically, this corrupt party may behave towards this honest party as if its input is 0 and other party's input is 1, whereas to the other honest party it might pretend, it might behave as if its input is 1 and other party's input is 0. So, you see this party is Byzantine, corrupt, and it is using different inputs for different honest parties. Towards this party, so let us call these 3 parties as A, B, C. So, A is corrupt and A is reporting to B that its input is 1, its input is 0. So, to B it will look as if A's input is 0 and her own input is 0. So, it is let us go and take 0 as the output, but towards C the same party A is now reporting that its input is 1. So, to C it will look like as if C and A together have inputs 1. So, let us go and output 1, and that will be a violation of the agreement property because B will be outputting 0, C will be outputting 1. So, consistency of the agreement property is violated. Now, you might be wondering that why can't B and C talk with each other in the protocol and find out that A is trying, whether A is trying to confuse or not, whether A is trying to confuse them, getting in conflict. So, if B and C talk with each other, then that is not going to help, because B will report to C that A has reported its input to be 0 and C's input as 1, whereas C will report to B that A has reported its input to be 1 and B's input as 0. Now, from the viewpoint of the party B, it is completely confused whether it is the party A who is lying or whether the party C who is lying, and same is the scenario from the viewpoint of the party C. C is totally confused whether the party B is lying or whether the party A is lying. So, this communication among the 2 parties, the honest parties, it is completely useless to find out who is lying, whether A is causing the confusion among them. And that is precisely is the intuition that why can't we design a perfectly secure BA protocol with 3 parties and one of them being corrupt. Of course, we can design a cryptographically secure Byzantine agreement protocol Okay. So, we can design cryptographically secure protocol as well as a statistically secure protocol with n equal to 3 and t equal to 1. There this argument fails, there this argument breaks, because we can have a protocol where every party associates a signature, its own signature, with whatever message it is communicating to other. In that case, this attack strategy by A fails, because if it is forwarding, if it is reporting its input as 0, so it will be sending a signed version of 0 to this party, and it will be sending a signed version of 1 to C. And now when B and C talk with each other, they will be able to conclude that indeed A is the source of conflict, because now B will be producing a signed 0 produced by A, and C will be producing to B a signed 1 again signed by A, and assuming signature forgery is difficult, B and C will conclude that indeed A is actually a corrupt party who has unnecessarily reported different inputs to B and C, and then B and C can take some default decision. But this argument of this method of using signatures and all completely breaks down, because if we are assuming perfect security, then in the perfect security regimes it is possible for an adversary to forge signatures. In that case, consider a scenario where A was honest and B is the source of confusion, and B might unnecessarily report to C that A has produced a signed 0 for him, even though A has produced a signed 1 for B. Okay. So, using signatures and other cryptographic primitives completely fails in the presence of computationally unbounded adversaries. So, when we are talking with perfect security, we can't use any such gadget, and that is why for perfect security this attack strategy will always work. Okay. But this intuition where A is the source of confusion, and to one honest party it might report a different input, and to another honest party it might report another input. This is very this is very intuitive, this is informal, we have to now formalize this argument. Okay. So, we now show formally that there exists no perfectly secure Byzantine agreement protocol with 3 parties tolerating one corruption, and the proof will be by contradiction. So, we will assume that suppose there is a 3 party Byzantine agreement protocol, I call it pi sub 3 BA, among 3 parties say A, B, C, and whenever I say parties, they need not be physical parties, they need not be living entities, they could be computers, they could be processes, there are some entities who actually run some protocol codes P, Q and R, okay, respectively. And this system has the property that if there are 3 such parties A, B, C who are running the codes P, Q and R respectively, and even if one of the parties get compromised and do not run the corresponding code, still the termination, validity and consistency properties are achieved. That is a guarantee given by this pi 3 BA protocol. We do not want to go into the exact details of pi 3 BA, it could be any round protocol, it could be doing any set of actions and so on. Okay. It is an abstract protocol. Now, assuming this pi 3 BA protocol, we design a new system S, okay, and this system S might look very non-intuitive at a first glance. So, let us first try to understand what exactly this system S is. So, this system S is not to solve BA, it is an arbitrary system, okay, where we assume that we have 2 copies each of A, B, C running codes P, Q, R respectively. So, we have 2 copies of A, I am calling them as A naught and A 1. One of the copies or one of the entities of one of the copies of A has the input 0 and other copy of A has the input 1. There are 2 copies of B, one of the copies has the input 0 and another copy has 1, and similarly there are 2 copies of C. Okay. And each of the entities, each of the copies of A, B, C is running the code PQR as per the protocol Pi3BA assigned. And in this system S there is no corruption. There is no corruption, okay. And each party will be knowing only its neighbors. Okay. So, for instance, A naught, it will be knowing that it is talking with C 1 and B naught. It will not be knowing that it is C 1 with input 1 and B naught with input 0. For him, for her it is as good as it is talking to a party C and to a party B. Similarly, from the viewpoint of B naught, it will be looking to B naught as if she is talking to the neighbors A and C, that is all. Okay. So, B naught will be not knowing that there is another copy of C, C 1, there is another copy of A 1 running in the system and so on. So, this actually models a scenario where every entity, every party has only a partial knowledge about its network. Okay. Unlike the Byzantine agreement protocols which we have discussed till now, where all the parties will be knowing the full network configuration, who is connected to whom and so on. Also, to every party in this system S, it will look as if they are a part of Pi3BC. Why so? So, for instance, let us consider this party P B naught, A naught and C naught. Sorry, let us consider the party B naught, sorry. Let us consider the party B naught. Then as per the protocol Pi3BA, B knows that it will be talking to an entity called A and to an entity called C, who will be running the codes P and R respectively with some input bits, and same is the scenario for B naught here. So, to this B naught, it will look as if she is participating in an instance of Pi3BA with a copy of A or with an entity A with some input, but running the code P, and an entity C who is running the code R. So, from the viewpoint of B naught, it will look like that A naught, B naught and C naught compromises a system of 3 parties running the codes P, Q, R respectively and participating in Pi3BA. In the same way, if I consider, say for instance, the entity A1, then from the viewpoint of A1, this triplet of parties B1 running the code Q, and party C naught running the code R will look like as if there are 3 parties running the codes P, Q and R respectively as per the protocol pi 3b and so on. As I stressed that this system S is not to solve the Byzantine agreement, but since everyone is running the codes PQR as per the pi 3BA protocol, and since this pi 3BA protocol has the liveness and the termination guarantee, that means after some specific number of rounds of communication ABC will have output. So, in the system S as well, each of the 6 entities will get an output, okay, as per the time specified in the protocol pi 3BA. That means the output is well defined. Output is well defined in system S. Now, even though the output is well defined in system S, what we are going to show here is that there exists an adversary strategy in the protocol pi 3BA, which will actually cause the system, which will actually cause the parties in this system S to output contradictory values, which will be a contradiction to the fact that output of the system S is well defined. So, basically what we actually are going to show is that the output of the system is not well defined, even though it should be well defined because of the liveness, validity and consistency properties of pi 3BA. Okay. And I stress that in system S there is no corruption. Okay. Now, what we are going to do is we are going to relate a system S with the properties that can be concluded from invocations of the protocol pi 3BA. Now, consider an execution alpha of pi 3BA where the party A and party B are honest and party C is corrupt. Input of A is 0, input of B is 0, and now what this party C does is the following. The party C, it mimics the party C1 as per the system S along this HCA. When I say along the HCA means to whenever it is communicating to the party A. That means in system S, C1 is not corrupt. I stress C1 is not corrupt because in the system S I assume that no party is corrupt. So, C1 with input 1 would have sent some messages by following the code R to A naught, and it will be continuously communicating to A naught as per the protocol code R, assuming its input was 1. So, when I say mimic C1, that is precisely what this corrupt C is doing during the execution alpha. So, for instance, if the first message sent by C1 to A naught was, hey, my input is 1, then in execution alpha C is basically talking to A and saying my input is 1. Then suppose based on whatever message A naught would have sent to C1, then C1 would have decided to send a set of new messages to A naught. Those will be the messages which C will be communicating to A in the execution of alpha during the next round and so on. Okay. Wherever while in the execution alpha towards the party B, this corrupt C behaves as if he is going to mimic C naught as in this system S. So, in this system S, this C naught was not corrupt, his input was 0 and it was running the protocol code R, and based on its input being 0 and protocol code R, it would have exchanged some messages with B naught. Those are the messages which it is precisely exchanging with B in this execution alpha. Okay. That is what is the strategy of this corrupt C party. Okay. Now, we know that this Pi 3BA protocol has the validity guarantee, and validity guarantee demands that if honest parties during the execution have the same input, then that should be the final output. So, what are the who are the honest parties in this execution alpha? It is A and B. Whether they have the same input? Yes. So, I do not care what exactly is the input of the corrupt party. To one honest party it is participating with its input being 1, to another honest party it is participating with input 0. The validity of Pi 3BA, that means the protocol code P and Q in the execution alpha, where the inputs of B would have been 0 and 0, which should have ensured that A and B output 0 irrespective of what messages C is communicating with A and B. Now, if we consider the view of the party A naught, entity A naught in this system S, it is identical to that of A. Now, what does view mean here? So, view means the messages sent and received by the entity. So, whatever A naught is seeing in the system S, that is identical to whatever A would have witnessed in the execution alpha, because in the execution alpha A would have talked with C1. Okay. That means, the messages it would have received from C will be identical to what C1 would have communicated to A naught, and the messages that A naught would have received from B naught will be identical to what the entity A would have received from the entity B in the execution alpha. So, that is why view wise the view of A naught will be identical as it is in alpha, and due to the same argument the view of the party B naught in the system S will be identical to the view of the entity B as per the execution alpha, because in execution alpha the entity B would have talked with entity A whose input is 0 running the code P, that is precisely A naught, and entity B would have talked with a corrupt C who is mimicking C naught, okay, with its input being 0, that is, and running the code R, that is precisely is the party C naught. So, to B naught it will look like as if it has participated in the execution alpha. Now, based on the views A naught and B naught have in the system S, they should output whatever the entities A and B should have output in the execution alpha. Okay. So, based on the views of A and B would have output 0 in the execution alpha, and since the view of A naught is same as that of A, and since the view of B naught is same as that of B in the execution alpha, A naught and B naught would output 0 in the system S. That is what we can conclude regarding the output of the entities A naught and B naught in the system S. Okay. Now, let us consider another execution of the protocol Pi 3BA, where now the entity A is corrupt and B and C are the honest entities, and A mimics the entity A naught towards C whose input is 1. Okay. So, basically this corrupt A is trying to mimic A1 along the edge AB. Okay. So, A1, let us see where it is A1. So, this is A1. So, whatever messages A1 with input 1 and protocol code P would have communicated with entity B1 with whose input would have been 1 and running the protocol code Q, same messages the corrupt A will be communicating with the party B in the execution beta. Whereas, whatever messages A naught with input 0 would have communicated to C 1 in the system S, those are the messages which A will be now communicating with the entity C in the execution beta. Okay. Now, again using the similar argument as we have done for the previous configuration, in this configuration B and C are the honest entities during the execution beta and they have the same inputs. So, it does not matter what the corrupt A communicates with B and C, the protocol code Q and R should guarantee that based on the views that B and C have, they should output 1 in the system in the execution beta. Now, let us compare what is the view of B 1 and C 1. The view of B 1 will be identical to that of B as per the execution beta, okay, because B 1 will be receiving the same set of messages from A 1 as it would have received from the corrupt A in the execution beta, and it would have received the same messages from C 1 as it would have received from the honest C during the execution beta. So, its view will be identical to whatever is the view of the B, and in the same way if I consider the party C 1 here in the system S, its view will be whatever is the view of the party C in the execution beta, because C 1 will be communicating to A naught, that is mimicked by this corrupt A, and C 1 will be talking to B 1, that will be anyhow what is the message, what are the messages which B is going to send to C. Now, based on the views that B 1 and C 1 have in the system S, which actually we have argued to be same as in the execution beta, B 1 and C 1 are going to output 1, because that is what B and C are doing in the execution of Pi 3 BA, namely the execution beta. Okay. So, now we have 4 conclusions. So, we have concluded that A naught should output 0, B naught should output 0 in the system S, C 1 should output 1 and B 1 should output 1 in the system S. Now, let us see another execution gamma of Pi 3 BA, where B is corrupt. Okay. And A and C are honest, and this corrupt B towards A, it mimics B 1. Okay. So, this corrupt B towards towards A it mimics B naught, sorry, towards A it mimics the B naught. So, whatever the honest B in the system S would have exchanged, whatever messages it would have communicated to A naught, the same messages this corrupt B exchanges with A in the execution gamma, and whatever messages B 1 would have communicated or sent with to C 1 in the system S, the same messages it sends to the honest C in the execution gamma. Okay. So, again now if we compare, if we consider the properties of Pi 3 BA, in this case in this execution who are the honest parties? A and C are the honest parties. Do they have the same input? No, they have different input. So, we can't trigger the validity property of Pi 3 BA, but the consistency property of Pi 3 BA guarantees that A and C should have a common output bit, say 0, it could be 1 as well, but that is determined by the protocol. So, what it means is that an execution gamma where A and C are honest with inputs 0 and 1 respectively, and where B is behaving maliciously towards one honest party, it is mimicking whatever communication B naught would have done towards A naught, and towards C it is mimicking the communication whatever B1 would have done towards C1 can't cause A and C to output different bits, right. Even if the corrupt B does like that, A and C should output the same thing. Now, let us see how it implies a contradictory behavior in the system S. If we see the parties A naught and C1 in the system S, their views will be now identical to that of A and C as per the execution gamma. So, for instance, A naught, let us consider A naught. A naught's input is 0 running the code P, that is what A is doing in the execution gamma. A naught is talking with C1 running the code running the code R with input 1, that is what A is doing even in the execution gamma. Now, the other neighbor of A naught is B naught, who is running the code Q with input 0, that is what the corrupt B is doing towards A in the execution gamma. And what about C1? C1 is talking with B1 whose input is 1 running the code Q, that is what the corrupt B is doing towards dishonest C. So, whatever A and C would have output in the execution gamma, that is what C1 and B1 should do. So, what exactly A and C outputs in the execution gamma? They output 0. So, that is why C1 and B1 should also output 0. Okay. So, C1 should output C1 and A naught should output 0, because we are assuming A and C to be honest. So, C1 and A naught should output 0, but now you see we get a contradiction, because we have already concluded that C1 should output 1 earlier, and now we are concluding that C1 should output 0 in the system S, and that is a contradiction, because now it shows that the system S is not a well defined system, because everyone in the system S is honest. Remember, in the system S no party is corrupt, they are exchanging messages based on the protocol code and whatever are their respective inputs. So, if there is no corruption, then the output should be well defined, because everyone is following code of pi 3ba only, but the well defined behavior is not there, because we are getting a conclusion that C1 should output 0 after time t, whatever is the time defined by the liveness property, and at the same time we are concluding that C1 should output 1 after the time t. How can that be possible in a well defined system? That is coming only because there must be some problem with the properties of pi 3ba, that means pi 3ba does not achieve all the claimed properties, and that shows a contradiction that pi 3ba does not exist, because if pi 3ba exists, then this violation of the well defined property in the well defined output property for S should not occur at the first place. Okay. So, that shows that pi 3ba does not exist. Okay. So, the reference used to derive at the impossibility result for n equal to 3 and t equal to 1 is explained in a detailed fashion in this textbook. It is also available in this textbook. Thank you.